Close, but not. This is still learning energy, potential energy also. One away, like one substrate, and now we're changing all T. Oh, yeah. So much goes into that one. See the heck of a okay, you missed one day in this class. Yeah. That's hard. What's that? Try to count this. At least 4 these. We have quizzes that both days. There was a lot. Yeah, it's not crazy, it's just a lot. Like, let's do it, go around this. That's right. What about? We can spend another. Lots of just in more energy conservation today. Yeah, just more energy conservation. Tactics to apply to solve problems. The more reason I say maybe it's a following kind of so it helps out explanation for it. Otherwise, why do it? It's good stuff. Maybe we explain that all get station spiritual stuff. Maybe an angel process. It was supposed to be on class.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing? Post midterm, hopefully everyone's feeling okay. Okay. So to begin today, just because I know it's after the midterm, first thing I'll say is that I've started grading your guys' midterms. I'm not anywhere close to done, but I will be done by Tuesday. And so, if you want to pick up your exam, I'll have them ready by Tuesday. It'll be on Canvas probably by Monday night. So you can expect that to happen. Okay. Right, so you guys can definitely expect that, and just because I know some people attend on Zoom, so if you want to come on Tuesday or even just stop by at the end of class, I'll have the exams ready by that time. Okay. I think also is this is also a good time to remind everyone of some important grading policies that we have in the class. So remember, we have 2 midterm exams. Right? And they're actually weighted differently for your final grade, right? And so one exam is going to be worth 30% of your grade. Right? The other one's going to be worth 20% of your grade. Okay. And the way I choose which exam is a higher weight of your grade is whichever one you do better, right? Right. And so, let's say that, you took the exam this week and it doesn't go as you planned. You have a chance to kind of make up that score and then some, for the next exam, which tends to be a little bit on the easier side. First exam for this class is always a little bit intense just because differential equations is, we cover a lot of ground and kind of in a relatively short amount of time for differential equations. So there's just a lot to study for the first exam. Second exam is a bit more straightforward. Probably all newer stuff, compared to the first exam, but it's a bit more straightforward, I guess you could say. Okay, so people tend to do better on the second exam in this class than the first. So, but if you already did really well in the first exam, you can think of that as like you already have 30% of your grade already secured. Okay. So if you don't do so well in this exam, just remember you can always kind of make it up. And I also have another policy. So I don't curve individual exams kind of in the traditional sense, but I will scale the grades by the end of the semester. And so what that basically means is that at the end of the semester, after all the grades are in, so final exams, homeworks, all the midterm exams, and everyone kind of has their final kind of percentage, I compute the average, right, for everyone in the class. And then if that average is below a certain threshold, so for 308, I like to have my average grade be around like 77, 78, 79%, usually kind of around a C plus. If it's below that threshold, the class average, I'll add points to everyone's grade until we reach that threshold.
It's not in that price grade.
No, it's based on the overall average. Okay. So, for the time being, whatever score you get on the exam, the homeworks, that's kind of the grade that you get. But just be aware that at the end, I tend to add points. I won't subtract points, and so if the overall class average ends up being an 84, I just say, great, you guys are really smart. Everyone gets the grade that they want. So I won't subtract points. That's just kind of an asshole move, but I will add points to everyone's grade if the grade is below. Okay. How many points I add, it really just kind of depends on the semester. So it's kind of hard to kind of tell at this point, but just generally you can probably expect at least a couple points at the end of the semester. Okay. Okay. So just because midterm happened on Tuesday, so I wanted just to remind everyone about this. Any questions on this, or just any questions on kind of anything that we've gone over so far? Okay. All right, and so plan for today is we're going to continue with our lecture notes on vector calculus, right? So we're kind of just doing an overview of, hopefully a lot of things that you've seen already. So we've done, we've been kind of focusing on the derivative operators. So we've done gradients, we've done partial derivatives, we did divergence last time. So there's one more derivative operator that we want to go over today called the curl, and then we're going to move on to integral vector calculus. Okay. Okay, so let's go ahead and get started. Okay, so the last topic for differential vector calculus is the curl of a vector field. Okay. Oh, I'm sorry. One more announcement. So I did post homework 4 today as well. So hopefully you guys have got the announcement from Canvas. So homework 4, you can get started on it. It's not due for a couple weeks, or I think it's due next Friday actually. So obviously the stuff we covered today, the stuff we covered before the midterm, and then next Tuesday as well. All that's going to be needed on the okay. Okay. All right. So let's talk about the curl. Okay. So the curl of a vector field, kind of as the name implies, it's a way for us to kind of measure how much the vector field is kind of turning or spinning. Okay. Because remember what a vector field is, right? A vector field is essentially a multi-dimensional function where a vector quantity is defined at every point in space. Okay. And so, we can have situations like this, right? Or let's say we have a two-dimensional field just like this, right? And at every point, we have some arrow that represents the value of the vector at that location. Okay. So let's say we have a vector field V, which in this case is a function of X and Y, right? So let's say that our vector arrows are going kind of around in a circle like this. Okay. So that's a very interesting type of vector field, right? And so, oftentimes we want to quantify how much spinning or how much circulation is going on in this vector field. So the curl was kind of a way to do that. Right? So this has immediate application in fluid mechanics. And so if you've taken fluids, you're a mechanical engineer, you may have heard of a term called vorticity or vortices or vortexes, which is a very important concept in fluids. And so, an operator like curl is really important for us to measure things like vortices, vortexes, and spinning, things like that. Okay. Okay. So computationally, the way that we take the curl is we simply take the cross product between our nabla operator and our vector field. Okay. So remember our nabla operator. Nabla is our kind of our upside down triangle. Okay. Where we don't, nabla is not a vector in the true sense, but we kind of treat it as if it were like a vector, right? So a nabla, we kind of treat it as a vector where its components are the 3 partial derivatives. We have partial x, partial y, partial z. Okay. Right. And we're going to take a cross product between that nabla and our vector field V. Okay. Which in this case, obviously, V needs to be a 3-dimensional vector field. So it needs to have components in x, y, and z. Okay. All right. So our V here is a vector field at Vx, Vy, and Vz. Okay. So we can go ahead and compute the cross product. And so remember the way that I remember cross products is to make this kind of imaginary 3 by 3 matrix. We have I hat, j hat, k hat. We're going to take the determinant of this matrix, right? And so second row is going to be partial x, partial y, partial z. Okay. And then last row is going to be the components of our vector field. So vx, vy, vz. Okay. Okay. So, this is the way I kind of symbolically remembered how to take the curl. But of course, if you want the straight up formula, we can go ahead and evaluate this matrix here. Okay. So we take the determinant of this matrix, we get the following. Right. So x component is going to be partial vz, partial y, minus partial vy, partial z. Okay. That is the I hat component, or the x component, minus partial vz, partial x, minus partial vx, partial z, j hat, plus, and then the z component here is partial vy, partial x, minus partial vx, partial y. Okay. Right. Okay, so that's how you take the curl, right? So obviously, you can only take the curl of a vector field. You can't take the curl of a scalar field. Because for curl, you need to have your three components, x, y, and z. Okay. Okay, good. So one thing to notice about the curl as well, right? So, if you kind of think back to our previous two operators, right? So on the one hand, we have the gradient. The gradient is an operator that increases the dimension of our quantity, remember? So you take the gradient of a scalar field, you get a vector field, right? So you kind of go up in dimension. And the divergence kind of goes the opposite way. So you take the divergence of a vector field, you get a scalar field. The curl is neutral. So the curl, you take the curl of a vector field, you get a vector field on. Okay. So curl is dimension neutral, I guess you could say. Okay. Okay, so let's do a quick example to where we can see how we can compute the curl, and then we'll talk a little bit more about the applications before we move on to integral calculus. But any questions just on the concept of the curl, or just any questions on this formula here? Okay. All right, so let's do an example. Okay, so let's define a vector field. So let's let our vector field V equal the following. Okay. So we need our three components, x, y, and z. So the x component will be y times z. Y component will be 3z times x. And the z component will just be z. And what we want to do is we want to compute the curl of V. Okay, so this is pretty straightforward. We just basically plug into our expression up above, right? Where we know this yz here, this is our vx, our 3zx, this is our vy, and our z, this is our vz. Okay. Okay, so we go and plug it in. We're going to take the curl of our vector field. Okay. I hat, j hat, k hat. Okay. Partial x, partial y, partial z, right? And then we're going to fill in the components of our vector field. So for the x component, this is going to be yz. For the y component, it is 3zx. And for the z component, it's just z. Okay. All right, and so let's go ahead and evaluate our curl here. So we're just going to plug in and just evaluate each of the small determinants here. Okay, so first we have the x components. We have partial x of our function z minus partial z of our function yz. Okay, so that is the I hat component. Okay. Next, we're going to subtract partial x of our function z minus partial z. Or excuse me, I apologize. So this so for the x component here, it's partial z of 3zx. I apologize, because then this one is vy that needs to go there. So that was a typo on my part. I apologize. Okay. And so for the y component, this is partial z of yz. Okay, that one makes more sense. All right, and then z component, we have plus partial x of 3zx minus partial y of the x component, which is yz. All right, and so let's go. We can go ahead and evaluate all these partial derivatives, right? Keeping in mind that, remember, if you take a partial derivative of a certain variable, but it's not there, it just ends up being 0, okay? So for instance, we have this partial x of z. This is just going to get canceled out because z is a constant with respect to x, right? Same thing with this one here, okay? So both of those are just going to go away, okay? Next, we have the z derivative of 3x of 3zx, and so that's going to be 3x, right? Right, and so this is going to be equal to minus 3z, or 3x, excuse me, I hat, okay, plus partial z of yz, that's going to be positive y, plus y j hat, plus partial x of 3zx, that's going to give us 3z. And then partial y of yz is going to give us a minus z. And so it's going to be plus 3z minus z, okay? Which of course is 2z. Okay, and so if we kind of write this in component form, we have a minus 3x, positive y, and 2z. So that's our curl, that's the curl of our vector field. Okay, so if you're given all the components of the vector field, computing its curl is very straightforward. You just kind of plug it into our form. All right, any questions on this example here? Okay, good. Okay, so I will kind of just we'll say a couple more words about the physical interpretation of the curl, and then we'll move on to integral calculus. Okay. So remember, the curl is basically used to measure how much a vector field is spinning. Okay. Which might seem like a very niche type of thing, or just like a trivia thing for us to know, but there's actually a lot of applications for this, especially once you get into angular dynamics, angular kinematics, things like that. Okay. So for example, right? One very common example that you'll see is a spinning object, a spinning rigid object. So let's say that we have, just to make things simple, let's say that we have a disk, just like that, okay? We'll say it's rotating, right? It's spinning with some angular velocity. So we're going to say it has an angular velocity of omega. Okay. Right? And so if you have this plate that's spinning, right, you can compute the velocity at any given point, right? And so let's say that this right here is the center of our disk, right? And then let's say if we go out to some point here, so we'll say this is a point P, right? And we'll say the distance between the center and P is R, right? What we can say is that the velocity at this point P is equal to the angular velocity multiplied by the radius, right? And so that's just basic our angular dynamics there. Okay? In fact, we can actually use this knowledge here to compute a vector field for the velocity, right? Because the velocity magnitude, on the one hand, depends on the distance between our point and the center, right? But the direction also matters as well, because the direction is going to go basically perpendicular to the radius, right? So velocity at that point is going to be right there. Let's say we draw another point, like right here. Okay? Our velocity at this point is going to be like this. Okay. Right. So our velocity field on this plate we can actually quantify it like the following. So we have our v is equal to minus omega times y, comma omega times x, comma 0. Right, so that accounts for both the magnitude and the direction of our velocity field, remember, which is always going to be perpendicular, right? I should say kind of parallel to the direction of the rotation. Okay. Okay. And so if you take the curl of this velocity field, okay, so we take the curl of our velocity field like this. So we have our matrix I hat, j hat, k hat, partial partial x, partial partial y, partial partial z. Okay. Then omega minus omega y, omega x, and 0. Okay. What you're going to find here is actually a very interesting result. So our result here is basically that our curl is actually constant, right? And so it actually doesn't depend on x and y. Okay. In fact, you can verify this yourself, and so you can kind of run through the calculation and just verify this. But the curl is equal to 0, 0, and 2 omega. Which shows that our curl here is a constant of value. But not only that, but it's a constant value that depends strongly on the angular velocity. Okay, so what does this tell us then? So if you're in a region of space, or if you're in a region where your curl is constant, right? That means if you stand anywhere on the disk, basically your curl is going to be constant. That means you have rigid body rotation. So kind of a small, result there, but one that's very interesting as well, because a lot of times, when you compute curl and you find that it's constant, right? A constant curl means that, you have a body that's kind of rotating as a rigid body, right? And a rigid body essentially just means that, the body, if you stand at one point on the body, there's every point from yourself to somewhere else on the body is going to be the same, just because it's a rigid body, it's a solid surface. Okay. Okay. Another really interesting situation is when you have a curl of 0. Question.
The way you said that, it sounds like if you stand close to the center versus the outmost radius, you'll have the same velocity.
Not the same velocity, but the same curl.
Okay.
Yeah. So velocity is going to be different. That depends on how far you are from the center. But the curl, which is you can see here is just a measure of the angular velocity, is going to be the same. And that kind of is consistent with how we think of angular velocity, because angular velocity doesn't have any. There's no distance units in angular velocity. Remember, angular velocity, the units for that is radians per second, or degrees per second, and radians, I guess, is not a real unit, and so it's independent of any kind of length scale. Yeah. So curl and angular velocity are very closely tied concepts. Yeah. Mm-hmm. All right, and then if you have a curl of 0. Right? And when I say 0, it means all 3 components are 0. This is also another special case in which we say that our velocity field is irrotational. Or I should say our vector field. I say velocity just because I'm a fluids person, but technically we're talking about the vector field. All right, so irrotational fields are actually very interesting. And what that basically tells you that is if you stand in the field, right, and you kind of follow the velocity line or the vector lines, you may translate, right? So you may move from one point to another, but you yourself are not going to spin. So it's actually fascinating. So kind of the image I draw for this is always like some kind of stick, right? So let's say you have a stick, okay, and it's floating along some kind of stream. Okay? So basically, the stick is going to follow the streamlines of our stream. Okay? So at one point, it's going to be here, right? Another point is going to be here. Another point is going to be here. Okay. Now, if our stream is irrotational, that means our stick may translate, right? So its centroid may move from one location to another, but its orientation is not going to change. It's going to be in that same kind of position, at all points within the stream. Granted that our stream is irrotational. Okay.
What does that happen exactly? Because I imagine a flow cause it also.
Yeah. So I think the most obvious case for this would be if you have a constant velocity field, right? So if you have a vector field that's all going in the same direction, right? So basically, there's no spatial variation. It's just the same velocity going the same direction at all points in space, right? And so if you're in a field like this, right? So let's say that you're a person just like that, right? You're going to move along with the vector field, but because there's no relative velocity, right? So there's no relative velocity change from from the top of your head to the bottom of your toes, right? Mm-hmm. So there's no mechanism to cause rotation in that case. It's just going to move your body forward. Right? That's essentially what causes rotation is kind of relative velocity differences from one point to another. You know, just like a spinning top, just like a rigid body rotation. But if there's no relative velocity differences, then we say the flow is irrotation. Right? So if you've taken fluids, you know, you may have heard that term thrown around a lot. If you take an electromagnetism, that there's the concept of irrotationality is kind of big there as well. You know, I don't know if I've had the concept kind of explained to me in this way, but that's essentially what it means. Because if you can assume that your field is irrotational, it lets you do a lot of really other interesting math stuff with the field as well. It lets you make kind of a lot of assumptions that kind of make things easy. Okay. Okay, any questions on the curl or irrotationality before we move on? Okay, all right, so that's it for differential calculus. So let's go move on to vector integral calculus. Okay. So for the next couple of lectures, you know, we're going to be reviewing, you know, all the integral operators that you can do on a vector field or multivariable functions. Okay. Okay. All right. So the first thing that we'll say is that, you know, when it comes to vector integral calculus, we're mostly going to be focusing on the big theorems. And there's essentially two theorems that we're going to work our way up to. So, you know, we may get to the first one today, but then, and then, you know, we're definitely going to do the other one next time. Okay. So the first one being Green's theorem. Okay. And the other one being the very famous divergence theorem. Okay. Now, hopefully, you know, those terms are familiar. You've seen them before. But, you know, I'm going to make the argument here that both of those theorems, we're essentially going to use them in a very similar way. Okay. Because they both kind of allow us to do something that's actually quite clever, quite interesting, in that they allow us to change the form of our integral from one form to another. Okay. So in the case of Green's theorem, we're going to change a double integral into a line integral. And in the case of divergence theorem, we're going to change a triple integral into a surface integral and vice versa as well. Okay. Now, why would we do this? So on the one hand, you know, it's part of it is for computational convenience. And so what you're going to see is that, you know, one type of integral is usually more convenient to compute than the other one for various reasons. But it also kind of helps us with physical interpretation as well. Because sometimes, you know, when you see a certain type of integral and the way that you interpret that integral, it's a little bit easier to kind of see what's going on physically versus the kind of the original integral form. Okay. So that's kind of what we're going to do. You know, we're not going to get to the divergence theorem today, but we may introduce Green's. But think of it like that. So think of, you know, this whole unit as, you know, taking the form of one integral and then allowing us to change to another using these theorems and vice versa. Okay. Okay, so let's start with Green's theorem, right? But we do have to do a little bit of preliminary work beforehand. So first thing before we go over Green's theorem, let's go over the concept of a parametrized curve. So parametrized curves don't specifically have to do with you know, don't specifically have to do with vector calculus just yet, but it is something you need to know to learn how to take a line. Okay, so a parametrized curve is basically a path in space that we parameterize with an extra variable. Okay, so it looks like the following. So basically the way that we express parameterized curves is usually with some path variable r, okay? And we'll say that our r is our function of some variable. So usually parameterized curves have just a single variable, which we often call t. Right, and so what we say is that our path here is usually a collection of coordinates, right? So it could be two-dimensional curve or a three-dimensional curve, right? Where each coordinate is a function of that parameter. Right? Okay. Right, and so as t changes, as our variable t changes, then so does our location along the curve. Okay. Now, I chose the wording for this very, very kind of selectively, right? So the kind of the key to understanding parameterized curves is that is a path in space. Okay. So at any given time t, right, and t is usually interpreted as time. At any given time t, our parameterized curve gives us a specific location or a specific point in 3D space. Okay. So visually, it looks something like this. And so let's say that we have our origin here, right? So let's do three-dimensional space, just like that, okay? Right, and so as t goes on, so t usually starts from 0. So as t proceeds from 0 up until some ending point, sometimes it's infinity, then our parameterized curve will trace out a path for that curve in space. Okay, so for instance, let's say that we start at the origin here, right? And our curve kind of goes up in space like that, okay? So the important thing for a parameterized curve is that there is a sense of direction, right? So usually we're proceeding in one direction along the curve. Okay? So usually we start, let's say we start the curve at t is equal to 0 at the origin, and then we arrive at t is equal to t, tf, the final t, okay? Right, and so it's literally the path that we travel from t is equal to 0 to tf. Okay? But it's not simply just making a straight path, because if we're making a straight path, we just make a beeline to our final time. But we may take kind of an interesting path to get there. So the parameterized curve allows us to do that. Okay. So R of t here shows the path that we take along that.
So it's basically almost kind of like a loss transform turning into a different dimension or different domain, so that you can find which way there and reverting back to functions.
You can kind of think of it like that, but the t there is kind of meant for time, right? So think of it almost like your GPS, right? So think of that like when you're taking your GPS somewhere, you're driving from one point to another, right? And let's say the trip is going to take you like 20 minutes. And so at any given time along that path, so like 5 minutes in, you're going to be at the crossroads of like not with a state college, right? And then 10 minutes in, maybe you're at on the 57, right? And so that time there, that t there kind of defines your time, and your location is your parameter, your location on the curve. The parameters. Yeah. Okay, so let's do a simple example, because all that is kind of theoretical kind of math ways to kind of think about it. But let's look at the parameterized path for a circle. Okay. Okay. So let's say our R of t in this case is equal to 2 cosine of t and then 2 sine of t. Okay. And let's say our z component is 0. So, we're going to stay in the xy plane. Okay. Okay, so from here, you can see that our x of t is 2 cosine t, our y of t is 2 sine t, and our z of t is 0. And so, we're staying in the xy plane. Okay, so this parameterized curve here traces out a circle. And so we can plot this in the xy plane. So this is our x component, our y component. Okay. I'm not going to bother with the z component because our z component is 0. And so if you plot this for various values of time, what you're going to see is that it actually traces out a circle. Okay. Okay, so let's start at t is equal to 0. So at t is equal to 0. Okay. Right, so we're going to plug in t is equal to 0 into our r of t there, right? And so r of 0 is equal to 2 cosine of 0, 2 sine of 0, and then 0. Okay. On the first component there, that's our x component. Our second component is our y component, and our third is our z component. Okay. Okay, so cosine of 0 we know is 1. Sine of 0 we know is 0, right? And so what we can say is that r of 0 is equal to 2, 0, 0. Right? So we can plot that point in our xy plane. So our first point here is right here. So this is 2, 0, 0. So at t is equal to 0, we're starting on the x-axis. We're starting on the x-axis with a distance of 2. Okay. Okay, so now let's plug in another value for t. Okay, so let's plug in pi over 2 for t. So at t is equal to pi over 2. Okay. So let's plug that into our r function here. So we're going to plug in 2 times cosine of pi over 2. Okay. And then 2 times sine of pi over 2. And then 0. Okay, so we go ahead and evaluate this. We have cosine of pi over 2, that is 0. Sine of pi over 2, that is 1, right? And so what we get from this is 0, 2, 0. So our second point here, so this is going to be t is equal to pi over 2, right? We end up at that point there. All right, so I'm only doing the poles there just because they're easy to do, but you can do the same thing for any value of t, right? And what you're going to see is that we're essentially tracing out this path. So we start here, right? So actually, let me mark the start point with the green thing. Okay? So we're starting here, right? And then we're going to trace our path along, right? So we go up here, right? Then we go down here, right? You can kind of see that when t is equal to pi, right, we're going to end up back on the x-axis there. And then we're going to rotate down like this, and then back to our origin point here. So you can see here that we're traveling along the path in this direction. Okay. So there is our circle. Okay, so remember with parameterized curve, it's not just the shape that gets produced, but actually the path that you actually take to get there. So that means you define where you start, which direction you're going, where you hit certain points at what time, right? All of that is important for the parameterized curve. Okay, any questions on this here? Okay, good. All right, so this type of curve is actually very interesting because you can see here that eventually we end up back at our starting point. Okay. It doesn't always have to do that. So you could have an open curve, which kind of doesn't come back. But for this case, we do. So since this curve ended up back where we started, we have a special name for these types of curves called a closed path or closed curve. Okay. Okay, and closed curves will have important properties for us, especially when we do grades. I thought I kind of mentioned that. Okay. Okay. All right. So that's the concept of a curve, right? So, as long as you're kind of tracing out a pathway in space, you can always parameterize it using a parameterized curve. Okay. Next thing we're going to learn how to do is compute the tangent to a curve. Right, so the tangent to a curve is exactly as it describes, right? And so at any given point, you can compute a line or the slope of the curve at that given point. Okay. And so if we wanted to compute the function of the line that is tangent to a curve, all we have to do, just like how we understand derivatives, is we just take the derivative with respect to our parameter t. Okay, so we're going to have dr dt, right? And essentially, we're just going to take the derivative of every single component of our curve. So this is going to be dx dt, dy dt, and dz dt. And so by computing the tangent, we're going to get a function here that tells us, a line that's always tangent to a curve, right? So going back to our circle example up there, right? If you take the tangent to this curve, you're going to get lines that kind of look like the following, right? So basically lines that are tangent to your surface at any given time. Okay, good. All right, so that's going to be important for us when we compute our line integrals. Okay, so now that we know what a curve is, a parameterized curve, now that we know how to compute the tangents, let's go ahead and apply this to compute a line integral. Okay, so line integrals are quite interesting. In a lot of ways, you can think of it as just the generalization of a one-dimensional integral. So a one-dimensional integral, let's say that we have a definite integral with a defined lower bound and a defined upper bound, right? So we can say that we are integrating from a to b of some function f of x dx, right? So that's an expression you've probably seen hundreds and thousands of times, okay? Right, so you can make the argument here that this is kind of the first line integral that you learn, right? It's just that the path for this integral is actually very straightforward. And so in this particular case, we're integrating between two x values, between x is equal to a and x is equal to b. Okay, so you can actually plot this, right? And so if you draw kind of a typical XY plane here, right? We can draw two values for X. And so let's say this is X is equal to A, this is X is equal to B, okay? Right? So by performing this integral, you can say that we're just integrating along the path that goes straight from A to B. Okay? So basically going just like this. Right? And our function f is, of course, going on in the back. Okay, so a line integral basically takes this idea, which for traditional integrals, we're integrating along a very simple path, and saying that when we perform integrals, we don't have to go along this very simple path. We can actually go on a very arbitrary path, a very complicated path. Oops. I don't know why that happened. iPad's ready to go home. I don't think so. Okay. All right, so line integrals allow us to integrate over any complex and arbitrary curve. Okay. Okay, and so instead of just integrating along just a boring kind of path from x is equal to A to x is equal to B, right? Maybe we're integrating along this curve. Okay? So we have 2 points arbitrarily in space, right? So we'll call this P1. And then let's say we're integrating along this path that kind of goes just like that. Okay? Right, so we can integrate basically along the path from P1 to P2. Right? So with our concept of parameterized curves, where basically our parameterized curve can go anywhere, right? So it can go anywhere in three-dimensional space as long as we parameterize it. Line integrals allow us to take advantage of this and integrate it along any particular path. Okay. Okay. So the way to compute it is like the following. Okay. So a line integral, right? So to compute a line integral, you do need some vector field f. Okay. Okay. So this f here is some vector field that we want to integrate. Okay. All right. What we're going to do is we're going to take the dot product between our vector field and the tangent of our parameterized curve. Okay, so we're going to take f dot product with dr. So this dr here is the tangent of curve. All right, so that's the shorthand notation for a line integral. I would say it's not that helpful just because it's there's no indication here of how you basically parameterize the curve or how the vector field is supposed to be, right? What you're even integrating over, right? It doesn't make sense that we have an integration variable r vector. That doesn't make any sense. So the form of the line integral that I like a bit better is something like this. Okay, so for this form, we're actually integrating between two explicit values. Okay, right? And the important thing is that we're integrating over our parameterized variable t. So we're integrating from one variable t is equal to A to another variable t is equal to B. Okay. T is our integration variable, so I'm going to go ahead and add a dt there, so that indicates that we're integrating over time, t. Okay. And then we have our vector field here, but we need to parameterize our vector field according to our parameterized curve. So this f of r of t here is our vector field. Parameterized with respect to t. Right, so that's kind of the key to the whole operation of computing a line integral, is how do you take your vector field and how do you kind of reparameterize it in terms of your parameterized variable t, okay? And we'll do practice with that. So, that's not supposed to make sense right now. And so, once we do an example, I think that'll make a bit more sense. Okay? And then we're going to take the dot product between this and the tangent to our curve. So that's basically the same expression we had up here. Okay? So we have d top product with dr, dt. Okay? Okay. So this is the form of the line integral I like a little bit better because it's it is a bit more cumbersome to write. There's a bit more to write. I think if you look at a lot of engineering textbooks, they'll favor the form on the left, just because it's more compact. But I think if you're doing it for the first time, you're trying to grasp the idea of a line integral for the first time. The form on the right is actually a little bit more useful. Okay. Okay. Any questions on that before we do an example of a line integral? Okay. All right. So let's do a quick example just so you can see how it all happens. Okay. So let's go ahead and compute the line integral. Okay. So to compute a line integral, you need to be given two pieces of information. So on the one hand, you need to be given your vector field. Okay. So let's say our vector field is very simple in this case. So f is equal to, and this is a function of x, y, and z. This is equal to z, x, and y. Okay. All right. So where this z here, this is fx. Our x here is fy, and our third component is fz. Okay. Okay, so that's a vector field that we want to take the integral of. And then you also need to be given the path along which you want to integrate along. Right, so the terminology kind of sounds like the following. So it's compute the line integral of this vector field along the following path. And so at this point, you're usually given some parameterized curve R of t, okay? And so in this case, we're going to compute our line integral along a helix. Okay? So this is cosine t, sine t, and 3t. Okay? Where this cosine t here, this is r, or I should just call this x of t. Our next component is y of t, and our third component is z of t.
It's 3t.
3t, yes. Okay, so basically we're gonna take these given information, take these two expressions, plug them into our formula for the line integral, and then just evaluate the integral from. Okay. All right. So first thing we'll do, just for the sake of visualization, you don't have to do this, and so I just like doing it just to kind of see. Is let's visualize this path just so we kind of know exactly kind of what we're integrating on. Okay, so you can see here our x of t and y of t. So that looks familiar, right? So if you think back to our example from earlier, that is going to trace out a circle in the xy plane, right? So as t increases, right, the x component and y component of our r of t is just going to be a circle, right? But at the same time, one thing that's different here is that our z component is going to be steadily increasing. Okay, so in x and y, okay, in x and y in this case, we're going to be basically making a circle. But in z, okay, right, our z component here is steadily increasing along that linear profile z of t. Okay. Okay, so if you plot this out, if you kind of visualize it, it may look like the following. Okay, so x, y, and z. Okay. All right, so our starting point is actually here. So, it's always helpful to think about where your starting point is. So when you plug in t is equal to 0, right, you end up with the location 1, 0, 0. Right? And then as time goes on, we're going to rotate. We're actually going to rotate counterclockwise like this. But we're not going to come back to where we were. We're going to steadily kind of increase here. And I apologize, this is a terrible drawing, right? But you can see here that in the XY kind of plane there, we're kind of just making a circle. But as we're making a circle, we're traveling steadily upwards. And so it kind of looks like a corkscrew, or it kind of looks like a helix. Okay. Okay. Okay, so that's the path that we're going to be integrating over, essentially. Okay. All right, so how are we going to do this? So how are we going to basically integrate this curve? Because if we look at our vector field here, or we look at our expression for the line integral, right? We're integrating over t, right? But if we look at our vector field right now, our f, right? F here is not a function of t, it's a function of x, y, and z. And so first thing we need to do is we need to basically reform f so that it is a function of t. Okay. Right? Otherwise, we can't integrate over. So a line integral is just a one-dimensional integral. So you can only have one variable for integration. Okay, so actually, let me go ahead, just so I'm not scrolling up and down. Let me go ahead and rewrite everything here. So we have f of x, y, and z is equal to z, x, and then y, right? And then our r of t here is cosine of t, sine t, and 3t. Okay. And then just also to remind you, our r of t, each component is basically that coordinate as a function of time. So cosine t here, this is x of t, sine of t here is y of t, and or 3t here is z of t. Okay. Okay. So the way we're going to parameterize f is we're essentially going to plug in each component of r of t into f of x of f into f, our vector field. Okay. So basically, everywhere you see x, you're going to plug in x of t. Everywhere you see y, you're going to plug in y of t. Everywhere you see z, you're going to plug in z of t. Okay. Okay. So what does that look like here? So that means, okay, we're going to reform f. So this is now going to be f of t. Okay. Or I guess you could say f of r of t, more specifically. Okay. because now our vector field here is going to be parameterized by our curve, right? So our first component of our vector field is z, right? So let's plug in our expression for z of t from our path into our vector field. Okay? All right, so we have z, and so our z of t from our vector, from our path here is 3t. Okay? So that there is going to be 3t. Okay. All right. Next, we have x, and so x, our x component of our path here is cosine t, and so that's going to be cosine of t. Okay. And then our last component for our vector field is just y, and so we plug in y of t from our path, and that is sine of t. Okay. Okay, so we've successfully parameterized our vector field in terms of our path coordinates. Okay. So that's always the first step you have to do is basically take your vector field and parameterize it in terms of your parameterized curve. Okay. Okay, any questions on that part there? Okay, good. I'm gonna do let me do one more just because this vector field is a little bit too simple. I think it's not the greatest example, right? So this is an aside. So this is something I'm just kind of making up right now, just to kind of show you just to kind of illustrate to you how to parameterize this. Okay. So let's say we have another vector field G of x, y, and z is equal to x squared plus y squared, and then let's say this is equal to 3xz, and then the last component there will be I don't know, y over x. Okay. We have a much more complicated vector field there. All right, and so if we were to parameterize this this new vector field according to our path, we're going to do the exact same thing as before. So everywhere we see x, we're going to plug in our x of t from our path. Everywhere we see y, we're going to plug in our y of t from the path. Everywhere we see z, we're going to plug in our z of t from the path. Okay. Okay, so first expression we have here is x squared plus y squared. Okay. And so we plug in for x of t. X of t we know is cosine t, so this is going to be cosine squared of t plus y squared, which is sine squared of t. Okay. So we're just plugging in for the coordinates exactly from our path, right? And of course, if you know your trig identities, cosine squared plus sine squared is just 1, right? So we can substitute that in. But our next component here is 3x xz. So we have 3 times x. X of t is cosine t. And then z of t here is 3t. Okay. So of course, that's going to simplify to 9t cosine t. And then our last component here is y divided by x. So once again, we take our y component of our path, which is sine t. Okay. So sine of t divided by x, which is cosine t, which is divided by cosine of t. Okay. Okay, so that was just an aside. So that has nothing to do with this example here, but just because we're running out of time, I want to kind of hopefully make it clear exactly how you parameterize a vector curve according to or vector field according to a curve. Okay. Okay. All right. So, but let's go ahead and finish this example. So let's go back to this vector field here. Okay. So to compute our line integral, the other thing that we need is the tangent to the curve. So let's go ahead and compute that. We're going to compute dr dt. Okay. So basically, we're basically just going to take the derivative of each component of our path. Okay. Okay. And so we do that and kind of reminding ourselves that our path is given by the following here. Okay. All right. So first we have dx dt, which is a derivative cosine t. So that's minus sine of t. Okay. And this right here is our dx dt. Okay. Next, we have the derivative of the y component, which is sine t. So derivative of that is cosine of t. This right here is dy dt. Okay. And then we have the derivative of 3t, which is just a linear function. Derivative of that is just 3. Okay. So this last one right here is dz dt. Okay, so now we have our parameterized vector field. Now we have our tangent to a curve. Now let's take their dot product. Okay. So f of r of t dot product with dr dt is equal to, okay. So our f of r of t is basically this expression up here. So we have 3t sine t, I'm sorry, 3t cosine t, and then sine t. Okay. And we're taking the dot product with our derivative that we have up there. So that is a minus sine t, cosine t, and 3. All right, so taking the dot product here, fairly straightforward. We're just going to match up the components and multiply them together, and then add all the results at the end. Okay. So the dot product here is going to be a minus 3t sine of t. Okay. Next, we have a plus cosine t times cosine t, so that's going to be cosine squared of t. Okay. Plus 3 sine t. Okay. All right, so now that we have our expression here, our last step is just to integrate this. Right? Because what we have after taking this dot product is we have a single expression here, which is just a function of t. So there's no x, no y, no z anymore. Okay. Right, so we take our integral of minus 3t sine t plus cosine squared of t plus 3 sine of t dt. Okay. And I think I forgot to give it to you in the beginning, but we're just going to do our integration along one rotation. Okay, so we're going to integrate from t is equal to 0 to t is equal to 2 pi. Okay, any questions on how we got to this point here with this expression? Okay, so the last step here is just to integrate this, and I say that as if it's a trivial thing. This is not the easiest integral to do. You do have to rely on some integration by parts, a little bit of trig identities here. Just in the interest of time, I'm just going to skip it, right? But I'll give you some hints here. So this right here, you're going to integrate by parts. Right? Cosine squared, integral of cosine squared t, you've probably done that at some point in a previous math class. But this is basically, you can make use of the double angle identity. Okay. Right, so basically you use the double angle identity to convert cosine squared to cosine 2 times t, and that is easier to integrate. And then 3 sine t, this one you don't have to do anything special, you just integrate this. All right, and so you do all that, and you actually get a very simple result. And so the result from this is 7 pi. Okay. Okay, all right, so that's all the time we have for today. And so when we come back on Tuesday, we'll introduce the idea of Green's theorem, right? What you're going to see is that in general, line integrals are kind of a pain in the ass to compute, and so we kind of want to avoid it when we can. And so when we can convert things to a double integral, that actually is easier, and Green's theorem allows us to do that. Okay. All right, so thank you guys for coming today. Remember, I will have your exams ready for you on Tuesday if you want to pick them up. I hope you guys all have a good weekend, and I will see you guys next week. There you go. See ya. Have a good weekend, Anthony. See you guys. Hi. Sir.
You for the advice or
Yes.
I saw that you do like in person as well.
Yep.
Is it better to do in person or do it
So if you do appointments, I do it on Zoom. Just because I'm at home during the time to take care of my baby. So just whatever's more convenient for you.
okay? Like during your office hours, is it like you're usually busy or?
Yeah, so office hours for the class, I reserve it for people asking questions with the class. But I do have walk-in advising from 2 to 3 p.m. on Thursday. And so if you want to do walk-in advising, it'll be next Thursday at 2 o'clock.
Good.
Yeah.
Thank you.